All right, let's start again. And we left off here with this array. Can everybody hear me? And everyone sees this Matzaget? Give me thumbs up.
Yeah.
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 Okay. Okay. So view, present. So we said you can declare something as data. I think we looked at the data in the simulator, and this says that it's a dot word. What does that dot word mean? Can anybody tell me?
It's a 4-byte number.
Exactly. That this number will take 4 bytes. I could have used the dot byte, and then it would have worked because all these numbers would fit in a byte. Notice I can have negative numbers. So my question to you is, which value will be in T3, in T5 at this line?
Six.
6. So you say 6. 0, 1, 2, 3, 4 would be this 6. How do you get that? Why do you say?
Well, I suppose it's the fifth position.
Why is 24 the 5th position?
It's -2, should be.
I think it's -2. Well, what are we doing? What we have to say, each one of these takes 4 bytes. So we have the first thing to do is take 24 and divide it by 4. What's 24 divided by 4?
6.
6. So it's as though I wrote the index 6. So let's just count. 0, 1, 2, 3, 4, 5, 6. It would be the number 4. Everyone sees that? Okay. So 4, the number 4 will get put into T5. Now, how does T3 point to the beginning of the array? Well, so we have the special command LA, which puts the address of lists into T3. So wherever list is sitting in memory, this essentially creates a pointer to that list. The pointer's name is T3, and as the register T3 has the address of that array, and I'm pointing to it. And I offset from the pointer 24 places. So actually I'm adding 24 to the value of this address. And I'm getting, if this address is 10 million, then this is 10 million and 24, and that will take me to here. This is 10 million, this is 10 million and 4, 10 million and 8, 10 million and 12, 10 million and 16, 10 million and 20, 10 million and 24. Okay. Let's look at another way to do the same thing. Look what I can also do. This is important also. Look, I can take 24, add it to 0. Look, it's an add I. So it takes an immediate value, 24, adds it to the register 0, which we said is always 0. I get the value 24, and I put it into T2. So that's like the 24 that I have here. Then what do? I take my T3, which is my pointer at the beginning of the array, and I add to it the T2, which is 24. So now if this was 10 million, this was 10 million over here, so it's 10 million and 24 puts into T1. So now I've got a pointer that's pointing directly to this 4. I got the address of this 4. So now I can actually get the 4 value by doing a load word into T4 from the new pointer that I created and offset 0. In other words, right where he is. That's what the 0 means. Don't move forward. So I did the same thing as I did over here, but I left the pointer being a 0. I left the index being 0. And that's going to be useful for us because if we wanted to loop through this array, we can't loop. This has to be an actual number like 24. We can't put a variable here. We'd like to put like our variable I, our counter, and we'd like to increment it each time we go through the loop. But the language doesn't allow us to do that. This has to be an actual immediate value. So what I'm going to do is I'm going to use 0 as my index always. And I'm just going to add to the pointer, like I did here. I added 24 to the pointer. I'm going to add every time I loop through 4 to the pointer. Is that clear?
You go back for a second.
Yeah. Question?
Why would you put before instead of 5?
Why would I put what? Why is this T4 and not T5?
Yeah.
No, that's just random. That's not important. This could have been T5. I just wanted
Okay.
I wanted to run this program, cut and paste it. Say I wrote comments here, and I actually wrote the comment symbol. I wanted to be able to cut and paste this code and be able to show you that T4 and T5 have the same value in it. So I wanted to put it in two different registers. But if I wanted to reproduce this exact example, I would obviously write T5 there. Okay. I'm going to skip this for a second, and let's start with our Hello World program. Everybody likes to have a Hello World. You need to set up certain registers to use a system call. So in other words, so first let me explain. I can make an array called hello, and it is of type ASCII. ASCII, you should know, means letters. So even though H is an ASCII value, like, well, it should be something like 75 or something. H, it should be like more or less than 75, like 73, because 65 is capital A. So this is actually a number, but I can write it as a letter and put it into the memory. Where did I put it in memory? At the beginning of the memory. Hello is pointing to it. What's the Z here? The Z at the end? That means that not only will it put hello world exclamation mark, after the exclamation mark, it'll also put the number 0. Now, the number 0 has a special meaning when you talk about strings. If strings are supposed to end with the number 0 or a null, same thing. So by having a null there, I'll be able to print it. Just like in cout, if you try to print an array of characters that's not a string, it doesn't have a null at the end, it'll just print a lot of garbage after the array until it hits a 0. I don't know if you ever came across that in C++. If you forgot to make your string be a real string, so the way cout works is it prints every letter until it sees a 0. So you need to put a 0 at the end here. So the ASCII Z, the Z here means put a 0 at the end. You can also have ASCII without the Z, then it won't put a 0 at the end. So I want to print hello world, and I've got my pointer. I need to make a pointer to this array. So the first thing I use is LA. LA is load address, and it makes A0 a pointer to hello. And then what I can do is I can put the value, look, add I. 0 plus 4 is, of course, 4. And that 4 I'm going to put into V0. Now, if I write the word system call, it's going to print hello world. If I write system call twice, it'll print hello world twice. How did it work? So notice that I have a pointer to a string. It's a pointer to a string in A0, and I have the value 4 in VF, and then it worked. So how did I know to do that? So we have to go back to the previous slide, and it says print string 4. And it says system call code that needs to be in V0. So what this table is telling me is that in register V0, I need to put the value 4 if I want to print a string. If I want to print an integer in V0, I'll put the number 1. So I'll put the number 4 in V0. And I also have to also look what it says here, arguments. A0 has to point to the string, has to be equal to the address of the string. If I have 4 in V0 and the string address in A0, then when I do system call, these are system calls, it'll know to print. So instead of having like cout and cin, we always write system call. It's just that the system call can be different things depending on what value I put in V0. I decide what the system call action will be based on the value that I put here. That's the way it works. So when I put 4 into the V0, that told that then what happened is that when I press system call, when I run system call, he checks what's in V0. He sees that it's a 4 and he says, oh, I better print the string. What string? Whatever string is pointed to by A0. He goes and checks what's A0 pointing to. Fortunately, I defined A0 as pointing to my string, so then he'll know to print hello world. That's how you
Back
do
to
it.
the system call table, it said for V0 equal to 1, then it would print an integer. So if you
That's fine.
had a string saved, the address of a string saved in A0, and then you called system call with V0 equal to 1, will it print the ASCII values of the string, or is it supposed to print,
All
try
right,
and
so
print
good
an
question.
integer?
What it'll print in this case will be the ASCII value. Well, theoretically, it will be of the H, right? You might think. But actually, it's a little bit complicated because let's look at this. Notice here I wrote the address of the string. Here I did not write the address of the integer. I wrote the actual integer. So the actual integer has to be in A0 when then you do system call 1. So if I would write over here, if I would write over here 1 to print an integer and leave everything else the same, what's it going to print? It's
The
going to
address of the H.
address, exactly.
memory.
Whatever is in A, the address of H. If I wanted to actually print H, I would have to load the letter. I'd have to do a load byte and then put it into A. I'd have to have another command here if I wanted to print that. But then again, it would only print the H, it wouldn't print the whole. If I wanted to print
Right.
all the ASCII values, I'd have to do a loop. When we want to print a string, we don't need to do a loop because it reads until it hits a 0. But since 0, it can't work that way when we're printing an integer because 0 is a valid integer. Okay, so now that was writing hello world. Now we want to do the opposite action, reading. Just a second. Yeah. Reading a string. So what we want to do here is we need to create space for the string to occupy. You can't just read a string and not put it anywhere. It wouldn't make sense. If you're reading a string, you have to put it into memory. So the first thing we do is we're going to make the string. That's going to be our label. And we'll create dot space means just give me blank bytes. How many bytes? So I asked for 64. I could have asked for 64,000, but I asked for 64. I figured that's enough. But whatever I want, I can ask for. Now I need to put 8 into V0. Now notice I did it with LI. Previous example, I put a number in with add I. So LI is just the same as add I, except that I don't have to write the 0 register. And the truth is it's pseudo assembly for add I something, which is a V0, 0, and the something else, which is the 8. So it's actually pseudocode, and so is LA. But these two pseudocodes we allow you to use in the lab because it makes life easier. I mean, this one's trivial. You could just write add I every time. But this one is a little bit more complicated to do without the pseudocode. So, like I said, we let you use these two pseudocodes. Now, essentially, this is saying put 8 into V0. Why did I put 8 into V0? Because according to this table, reading a string, which is what I want to do, requires that 8 should be in the V0. So I followed instructions. It also says something else. It also says A0 should be the address of the buffer. A buffer is a general term in programming to mean a space, some kind of space for input. You had that same issue in C++. You can't do C into a variable. If you want to take a string into a variable, you need to have first. You need to create an array that the string will go into. That what he types will go into. So the A0 will be pointing to the address of whatever buffer space I've created for the string. And here's another interesting thing. A1 will be equal to the length of how much maximum I can read. In other words, I don't know, he might type 1 letter, 2 letters, 3 letters, but I don't want to let him type more than the size of the array that I gave to him to use, that I allotted for him. So in this case, I'm going to put in A1 64. That's the size of the array that I made, the space that I made. And the A0 has to point to the string. So I use LA. LA creates a pointer. So now we're pointing to the beginning of this buffer. And we've told it the size is 64. And now I do system call. If I do this, I'm going to see nothing. And the system will wait there, blinking kind of, until I type something and hit enter. And whatever I type will go into the space that I defined up here. Now, we should explain a word about the number, how much I can actually type if I have 64. I mean, 64 is just an example. I could have done 255 or any number. So, but what are these notes that I have here? Note that the terminating new line, enter, will be read. It will be read and a null will be inserted. So we actually have 62 usable characters. So let me explain that. If I type, for example, hello mother and hit enter. So hello, let's say takes, 5 letters plus the space is 6. Mother takes 6 letters. So that's 12. So you might think that only takes 12 bytes, but it doesn't, because I hit enter at the end. And what happens is he has to read that enter. Somebody has to read that enter to know that I hit it. So when I hit that enter, it actually goes to the string. So the string actually gets the enter that I typed. It also, since it's read string, it knows that it has to put a null at the end, because the definition of a string is an array of characters with a null at the end, with a 0 at the end. So he's going to write a 0 at the end. So if I write hello mother, it's not going to be 12 characters, it's going to be 14 characters. So if I wrote 64 as the size, then really the person can only type 62. If he types more than 62 letters, they'll be cut off. I'll only get the first 62 letters that he typed. Then there'll be well, actually, no. Depends. If he types exactly 62, then I'll only get those. But if he types 63 letters, then I'll lose the null. I won't get the null in that case, because the null, whatever the last letter is, he's going to replace it with a 0. In that case, I wouldn't get I wouldn't get the terminating enter. If you type 64, 65 letters, the terminating enter will be lost, which is fine. The real problem is when he types less. I'm going to get this extra enter that I don't want, and we'll have to remove it. Okay, so that's how I read a string. Now, even though I didn't explain to you the other types, I'll explain to you the J type here. This is a jump type. It's an unconditional jump. It means the program should go to or jump to a different section of the code. There are only 2 commands of this type, the jump and the jump and link. So the way it works is like this. I put the opcode here. The first 6 bits tell me which command it is. So there's a special command for jump, or JAL. There's one for this and one for this. And then here is the address of where I want to jump to. So that's going to be useful. We'll use it in a minute over here in this example. But before we get there, that's the general explanation. And I have to make another general explanation. And then we'll see another example. We need to be able to make our programs act differently based on different data. In other words, if he types 1, it'll do this. If he types 2, it'll do that. We're going to give him a menu. In high-level languages, it's achieved with the if statement. So we normally use an if. But we don't have an if in this language. So in assembly, we have 2 branch statements. Branch means like the same way that a branch is a side branch from the main trunk of the tree. So a branch here means the code will process a different set of lines of commands if a certain condition happens. So that's why they call it branch. You can think of it as an if. Branch if equal, BEQ, and branch if not equal, BNE. Branching means moves to a new section of code or branch. So that will allow us to jump also. Jump over here, jump to this section of code, or jump to that section of code. BEQ and BNE are I-type instructions. That means they have exactly 2 registers. So let's look at an example. Here I wrote 1 line of C+ code. If I equals J, notice these are all similar examples. If I equals J, then F should equal this addition. Otherwise, F should equal this subtraction. Okay, simple. If I equals J, then F equals this, and otherwise F equals this. Now I quoted a quote. This is a quotation from the book. In general, well, we'll see this. Actually, I'll read. We'll see that this is done in this example. But in general, the code will be more efficient if we test the opposite condition to branch over the code that performs the subsequent if then if. So he says the code will be a little. Efficient just means shorter. The code will be a little bit shorter or a little easier to read if I would say if this is equal. If this is not equal, then do this. Otherwise, do this. So let's see. If I and j are not equal, then do f equals -1. In other cases, i.e. when they are equal, then do this. So let's see how we do that. Branch not equal S3 and S4. So we're assuming S3 and S4 are I and j. So we're saying if I and j are not equal, go to label else. Now else, it may sound like a keyword in language, it's not. It's just my own label. I could have called it cuckoo or fufu, but I called it else because it's kind of like an else. It's the else over here. So let's see that again. If S3 is not equal to S4, that means not if they're equal. If they're not equal, well, according to this, if they're equal, it does this. If they're not equal, it does this. So if they're not equal, then jump, branch to else, which means do subtraction. Subtract S1 and S2, put in S0. Well, that's great. But what if they were equal? Then it wouldn't jump to here. It would jump to here. It would just do the next line of code. This is only if they're not equal, jump to here. So if in every other case, i.e. when they are equal, so then do the next line. And look at this is an add. So that's like saying if they are equal, do the add. So you see, I first tested for the opposite of the condition, but I left the code in the same order. There's the addition is first and then the subtraction. So if they are equal, then I'm going to do this addition, which is exactly what it says up here. And then what am I going to do? Well, if I wouldn't, the problem is I might go to this and do the subtraction also. It's the next line of code. So in the middle, I've got to put another command called jump exit, which is an unconditional jump that takes me to here. So can I mark this? No. Oh, I have a way. Just a second. I have a pen that I can use. So this says if they're not equal, go to else. Otherwise this will happen. So let me put an arrow here. This says, well, if they're not equal, so if they are equal, do this, and then jump to here.
By the way, we don't see anything that you're writing or
Oh,
doing
you
on the
don't?
screen.
So stop share. Oh, let me do. Sorry, thank you for telling me that. Stop share. Share. Now you see it?
Yeah.
Yeah. So that's what I was showing. If it's not equal, jump to here. If it is, sorry, if it is equal, do this automatically. You don't need to jump to this line because automatically it goes line after line. But now you're gonna get a problem. After it did the behavior for equals, it's gonna also do the behavior for not equals. So I insert this unconditional jump. If I got here, then jump to the end. Now exit is not a keyword. It's just the name that I called the end. I could have called it end, could have called it soph, whatever I wanted. So that's two kinds of jump. The branch jump, which actually checks the condition, and the jump without a condition, unconditional jump.
All the words that are preceded by a colon is user-defined words, basically, in
Yes.
this language.
Yes. They're called labels. They're called labels, and yes, they're user defined. Okay, so let's do another example. Now we're getting into actual loop. This will help you with the homework. Find the first element not equal to k. All right, it's kind of a weird question. Find the first element in the array that does not equal k. In other words, it could be the k is 1 and the array is 1, 1, 1, 1, 1, 7, 1, 1, 1, 1, 1. So I want to find the first element that's not equal to k. I want to find that 7. So that's what it says here. While the array is equal to k, then increment it. Then I increment. So it'll keep going. The minute it finds one that's not equal to k, it'll stop, and I will be the value of that index that was not equal to k. So how do I do that? That's one line. That's a one-line loop in C++. That will define I as the location of the first number that's not k. So how do I do that in C++? So we're going to do it in a little bit of a, this is an example from the book. It's a little bit of a dumb example. Wait, did you see this example with Avi? I don't know how close he is to the book. Anybody tell me? You don't know.
I don't think we saw it.
No, okay. So let's look at this example, because this is also going to teach us some new commands. So we're not defining, notice we didn't define the array. We're assuming we have an array. Assuming S3 is the I, and we're jumping by 4 because we're assuming it's a int array. So let's look at the first line. The first line here is SLL. That's a new command. Shift left logical. What it means is take the bits in the number and shift them to the left. So for example, if I have, for example, let's say like this. Let's say I have, I'm not going to draw 32 numbers, but let's say I have a lot of zeros over here. And then I have 1, 1, and that's the end. So over here, there's a whole lot of zeros, okay? 32 minus 3 zeros. So 29 zeros. 29 zeros followed by 1, 1. Or, 30 zeros followed by 1, 1. So what's the value? Well, 1 and 2 is 3. Shift left logical will mean push everything over. And this last 0 that's over here, what happens to him is he falls into the abyss and he's gone. He just falls over. He falls out. He's no longer around. But what I shifted everything, what filled in over on the right over here? If I shifted the letters to the left, what happens over here is that a new 0 gets put in. So now my number looks like that with a whole lot of zeros, one less than it was before, because it's still 32 digits. So what's this value now? Well, 1 is no longer, it used to be 3. Now it's 2 and 4 is 6. What's the relationship between 3 and 6? What's the ratio or the relationship?
2.
2, exactly. It's twice. Now, let's say I do another shift. Another 0 falls into the Tehom, and another into the abyss, and another 0 gets put over here. Sorry, I drew that a little bit badly. So I got 2 zeros. So now this is 1, 2, this is 4. 4 and 8 is how much? 12. What's the relationship between 6 and 12?
2.
Also 2. So you see that by shifting left, I double something. If I shift it left twice, I multiply it by 4. I can actually do multiplication this way. And sometimes the compiler, if it's smart, and it notices you're doing something like multiply by 2, instead of calling the very lengthy process of multiplication, which there's a special chip for, instead of doing that, we'll just shift something 2 places, and it's much faster. So what I did over here is I shifted it. This number over here means how much to shift it. So when it says 2, it means shift it 2, which means multiply by 4. What am I multiplying by 4? S3. S3 is my I. Why am I multiplying my S3 by 4? Because my array, I really don't want to, I'm doing I plus 1. So I is going up by 1 every time, but I really want it to go up by 1, by whatever value it is times 4, because I want to jump in 4s because it's an array of words. So so assuming that S3 is my I, and it's whatever value it got in the beginning. Let's say it got the original value was 7. So it was at the 8th place in the array. But I really now want it to go, not to the 7, I don't want it to be 7, I want it to be 7 times 4, 28. I want to go to the 28th place in the array. So I'm going to shift it by 2, 7 will become 28, but I'm not actually changing the number. I'm copying the result of the shift of the 7 into here. So 21, I'm sorry, T1 will become 28. It is the result of the act, just like add is this register is always the result of the processes that happen on the right. If I had 2 adds, I would add them and the result would go here. This variable, this register wouldn't change. So actually I'm preserving the value of I, not changing it, but I'm putting the multiplied by 4 value into T1. Then I am taking the T1. Now let's assume that S6 is the pointer to my array, is equal to array over here. So S6 is my array, and I want to get my offset. So the way you do offset is by pointer arithmetic, which means I'm going to take my S6, add to it this new number that I got, 28. And I've already jumped through my array over to the 28th location, which is the 7th location, or whatever. In this case, whatever I is, I'm assuming I is 7. So I'm going to go over to the 28th place. So I'm going to add the pointer. Now, I don't want to change the pointer. The pointer is going to stay the pointer. I'm just going to take my 28 and add it to it and make a new pointer called T1, which points to the location of the element that I'm interested in. So I've preserved my array, my pointer to my array never changed, and I preserved my I. But I got this T1, which is now this new pointer, which points to the exact element I'm interested in checking. The next thing I got to do is load it, load the value at that place. So I'm going to say load word. The index is going to be 0 because I'm actually going to where the pointer is exactly pointing, because I've already incremented it by pointer arithmetic. I've added 28 to it on that pointer that I just created, on that temporary pointer. And now I put it into the temporary variable T0. So I've got now whatever value is over here. So I did a lengthy process just to get this, but I did it for a reason. Well, if you think about it, this is what the compiler does. This is how the compiler will translate this code, because he can't assume anything. He sees that you created a variable I and you incremented it by 1. He's got to do that. He can't just change it to increment it by 4. He's got to do exactly what you did. So if you notice over here, remember S3 is I. So look over here. Here's my incrementation. S3 equals S3 plus 1. So I incremented just like I did over here. And now I jump back over to here. I go jump loop start. And again, I shift S3 and I copy the result into T1. So I multiply it by 4 again. So I've actually got what's going on here is I is going up 1, 2, 3, 4. But T1 is going up 4, 8, 12. And you can say, well, why didn't he just take T1? Why didn't he just have one variable and do the increment by 4? Because then I wouldn't preserve the actual behavior of your program. You wrote your program that has a variable called I. Maybe you want to use that I later. Maybe you're going to print out that I. You need, at the end, you're going to print out 7 or 12, whatever that value is, not the multiplied by 4. So I need to preserve the original counter. Of course, this is an example of how if I would write it in assembly, I might write it more efficiently than the compiler. I might just have one pointer and multiply it by 4 and add 4 to it every time. And at the end, when I want to print out, I might divide by 4. By the way, you can divide by 4 simply by shifting right instead of shifting left. Shifting left multiplies by 2 each shift. Shifting right divides by 2 each shift. So I could do it more efficiently if I wrote it in assembly, but here I'm trying to show you exactly how the compiler would handle a compilation of this. Now we didn't finish. So this is the number loaded in, this is the incremented pointer. This is the value at that location. Now I need to do this check. Is it equal to K? So we're going to assume that K is in S5. So S5, is it equal to, here we're using the branch, our new command that we learned. Branch, we're saying not equal. NE is not equal. Is it not equal to K? This number that we got at that place in the array. Remember, we're checking 1, 1, 1, 1, 1, 12, 1, 1. So is it not equal to 1? Is it not equal to our K? Here's our K. So if it's not equal, then we're done. So jump X. Notice the condition is the opposite. Just like in the previous example, instead of I'm checking for equals, I'm checking for not equals. Usually that's what's going to happen. You're going to switch the condition. I mean, if you're going to translate from C++. So if it's not equal, jump to the end. If it is equal, so it'll just do the next line automatically. And then I add 1, and then I automatically jump to here. So here I got a loop exactly like this. So you see, one line of complicated C can become, 7 or 8 lines of assembly. Question?
Would it be possible to go over the shift left? Why is that timed again? I guess I'm missing.
Sure. So, oh, come on. What number is this? Chaim.
And what base? In regular.
Binary. Base 2.
Okay. 3.
What number is this?
Oh, I see now. Okay. Yeah, that's 6.
And one more. What number is this?
12.
Right. So it started off in 3, then it became 6, then it became 12. Every time I add a 0 to the right, I multiply it by 2. And the way I add zeros to the right is by physically moving the bits to the left and putting in the empty spaces zeros. Because I can't just stick in, if this number is at the right end of the number, I can't put a 0 there. It's already at the right edge. I got to shift it over and then I can put the zeros in. We call it shift.
The shift and the number 2 over there is shift 2 to the left.
Exactly. This means shift left logical, because there's 2 kinds of shift left. But I'm not going to talk about that right now. But there's shift left logical, and that shifts it to the left. And then how many? 2. And what am I shifting? S3. And I'm not changing S3, but I'm copying the result of that into what variable? T1. So T1 will have the result of that calculation. S3 will never have been actually changed.
So I'm really shifting 2 zeros at a time.
If I
Two.
write 2, I could write 12 here. Then I would be shifting 12 at once. I don't have to write 2.
S
I could write 1.
S3
Yeah, S3.
is S3 the address of the array?
No. S3 has nothing to do with any array. S3 is I. Just like I is an integer, S3 is an integer. The address of the array is
But then you're going to use the
S6.
number you get from S3 as the address of the array, and that's why you're loading into T1. Then you're going to use that as the address of the array.
We're going
to
to
get
add
to
it
the
to
array.
the we're going to add it to the address of the array. If the address of the array is 10 million, then I add my, my shifted result here, which is, let's say, 12. I add 12 to 10 million, I get 10 million and 12. And then I've got T1, which is 10 million and 12. I can use it as a pointer. But S1 at this point, it's a little bit confusing here because this line is a little bit strange. It could have been 2 different variables, but these are the same variable. At this moment, before this command finishes, S1 starts off being, let's say, 12, the shift 2 of some number. And I add it to 10 million. So I got 10 million and 12, and I put it into T1. So T1 used to be 12, but now I've overwritten it with 10 million and 12. So it's a little confusing. I could have used a different variable, but since I'm finished with T1, I don't need to use it again. I don't need to use that 12. It's meaningless to me. I just want to get the 12 plus the 10 million. So I don't have to use another variable. I can just overwrite my variable. That's efficient. I don't need to keep garbage around.
The second time over, if it was 10 million and 12, so wouldn't it be now like 20 million and 24 or whatever?
No, because I'm not shifting to 12 million. When I come back the second time, I go back to my original S1, which, remember, I never changed it over here. S1 stayed what it was, only T1 changed. S1 is still, 6.
Right,
So-
T1 changes every time from at the beginning. I see. Okay.
Yeah, so this is 6, and then T1 became 12, and then T1 became 10 million and 12, and then I go over here, and my 6 became 7. Now I go up to here, and I take 7, and I shift it twice, it becomes 14. Oh, no, it doesn't become 14. 7 shifted twice. What did oh yeah, I'm sorry. I give you a bad example. It was 3. It was 3 became 12, right? I got confused. 3 became 12 because I shifted it twice. 3 became 6, then it became 12. So now 3 became 4. 4 went over here, and I shifted it once, that became 8. I shifted it twice, it's 16. So T1 is 16. Then I added to 10 million, it's 10 million and 16. Well, that's exactly the next one after 12. 10 million and 12, 10 million and 16. We're jumping by 4.
I'm a little bit confused how I would check for the 0th spot. If we start off at the 4th spot, how is that not already like the second one?
Well, I don't know what I is. Just in this code, I don't know what I is. Like, it doesn't say what I is, just a variable. So I'm just assuming it's 3, just for the sake of figuring this out. But it could be anything. And then if it was 3, then it'll become 10 million and 12. And then the next time we come 10 million and 4 and 16. But did I answer your question? I'm not sure I understood exactly what you asked.
There's no way to check, meaning I was asking if we're looking for K when it does not equal. If we're starting with how you would start to compare with where K would be, where I would be like 0, let's say, where I would be 1, 2, 3.
Well, we're missing, just like this line doesn't give an initial value. This line in C does not tell me what the initial value of I is or K. I'd have to add another line here. Int I equals 0. Int K equals 12. So if I did that, then I'd have to add lines here too that are equivalent. And what would the equivalent to int I equals? Can anybody tell me what the equivalent of int I equals 0. How would I do that?
What was it? IL, or I think
Li,
that was
exactly.
a shorthand.
Right. We can just do the shorthand version. Where was it? Here. Li T0, whatever variable we want, 0. If we wanted to give it the initial values. Or we could do it the long way with add I. And then the register 0, which is always 0. 0 plus 4 is 4, goes into whatever number we want.
Say that again. The register that's what's always 0.
Register 0 is always 0. So there's a register 0 here. If I want to remember, there's 32 registers. One of them is called 0, with the actual name ZERO. Let's see. So we did the string, we did the jump decision, we did this branch example. Now let's do a bigger example of looping through an array and printing it. Here is a complete example. This is probably something you want to see because it's similar to the homework. Here I make my array of some numbers. Now I write dot text to indicate that it's an array definition here. Dot data, and dot text indicates that it's the code, the actual program. First thing I do, anyone tell me what this line means?
Load
The
address of my array into
S3.
register 3.
Exactly, S3, S3. And what do we call that in C++? What is S3? What does S3 refer to?
A
Pointer.
pointer.
Yeah,
Reference?
exactly. That's a pointer. Now we come to loop start, which is a label, doesn't do anything, it just indicates a place in code. Then I do 1 goes into V0. And I wrote here in a comment for printing integer. As that's according to the table that we learned, that is how I printed integer with V0 has to be 1. Now I have to put into A1 the first number I want to print, in this case 34. So since I've already got the pointer to the array, I'm going to say 0th place in S3, which is pointing to the first one, and copy it into register A0, which is exactly where I want it to be for my syscall to work. Then when I write syscall, it's going to check that V0 is 1. Say, oh, you want to print an integer? Let me check A0, and it'll see 34 there. It'll print 34. So I've succeeded already printing the 34. Now I'm going to check if I'm finished. Now what I did here was branch equal. If A0, which is the value that I just printed, if it's equal to 0, then jump, BEQ is branch or jump to the end, and I'm done. So basically what I'm saying is, if this would be a 0, I'm going to be finished. Eventually I'll get to the 6, and then I'll print the 0, and it will be a 0, and I'll know that I'm done. So I'm using 0 as the indicator instead of a counter. I'm using 0 as the indicator, and as I could also, whenever you want to print a loop, you either have an indicator in the array, or you have a counter that you, from the beginning, from the outset, I want to print 10 things, so I'm going to make a counter to 10. But here I'm not deciding ahead of time. I have an indicator inside of the array, 0. So if it's 0, finished, done, go home. But if it's not, then I want to print a space because I don't want to print all my numbers next to each other. So I put into A0 quote space quote. There's a space in between there. Single quotes, just like in C++. You could define a variable with single quotes. You can do single quote A, and then the variable get the value A. If it's a, yeah. So I load the space into A0 and I put it to V0 11 and I do syscall and that's going to print me a space. Now, how did I know that? Well, if we go back to the table, 11 is print character. Single character, not print string like we have with 4, but print a single character. And here I don't need pointers. I just say, notice here I have the address of the string. Here I have A0 is the actual character I want to print. The very character I want to print, not a pointer to the location of the character, but the actual character to print. So that's what I put into A0. Over here, a space. So A0 is the actual space I want to print. And then V11 is print character, and then I printed it. So now I printed a space, I printed 34 in a space. Now all I've got to do is continue the process. So look what I did. I did not do it the way we did in the previous example. I didn't do this complicated thing of taking the incrementing by 1 and then multiplying it by 4. And because I'm writing directly into assembly, and all I want to do is print I don't need to keep track of that number. So what I'm doing is I'm taking my pointer. Remember we said that S3 is a pointer. S3 is a pointer to the beginning of the array. And I'm going to always print at offset 0, but here I'm going to do pointer arithmetic. And I'm going to increment my pointer so it points. If it pointed here, it's not going to point here. And now it's going to point here. Each time I'm pointing to the next location in the array. So I'm going to add 4 to it because it's a word array. If it would be a byte array, I would add 1 to it. It's a word array. I'm going to add 4 and then jump loop start. I go all the way back to here. And again, I put V1. I put 1 into V0 because last time I put 11 into it. I need to overwrite the 11 and put a 1 there for printing an integer. And I need to reload A0 with the 56. So that's going to be the 0th place of the incremented pointer, S3. So now I got the 56. And then I'll print it. Then I'll print a space. And I'll keep going. And I'll check every time if the number I just printed was 0. Is that clear? Or do people have a question on that? So these slides, you can look at these again. These slides are on the Moodle. Oh, I skipped that example, right? Okay. That's interesting, actually. Branch example. Yeah, I like the way I did that this time. I never did it that way before, but I think I want to switch the order of those slides. I like that. So I do the branch example from the book, loop example from the textbook, and then my example. And then I'm explaining here why it was more complicated, and I just explained that to be close to the way the compiler translates. That's why the book does it that way. It's just showing you how the compiler would do it. Okay, mult is for a later. I mean, I can mention it for you. Well, I'm not going to mention it. It's a bit complicated, but mult is for multiplying. You don't need to do that right now. Division, you don't need to do. Some more operations. This is very important, extremely important. Set less than. Because if you noticed, we had branch on equal and branch on not equal. What if I want to do a branch where it's less than something? If it's less than this, then go here. Or if it's greater than this, go here. So there is no branch like that, actually. Here we see, well, here we see some. There are some. Branch on greater than 0. Branch on greater than or equal to 0. Branch, these are special commands. Branch on greater than or equal to 0 and link. Well, we don't learn that yet. But essentially, branch on greater than 0, branch on equal to 0, greater or equal. Branch on less than 0 or less than or equal to. So we've got these branches, but none of them are like branch on less than 12. How do I do that? branch on more than 20, branch, and as long as it's less than 30, whatever I want to do, I can only do with 0. So the answer is we have another command to help us with that. And that is set on less than. And it's a very clever little command. What it does is it says like this. Let's say I give it S and T. You see, it's a pseudocode. I give it S and T, and D will get the value. What value will it get? It'll get either 0 or 1. What determines whether it gets 0 or 1? The relationship between these two variables. So, for example, well, not for example, here, paradigmatically, D will be set to, set means 1. Unset means 0. 0 is like, it's not set. Set is always 1. That's what the word means in computers. So set, D1 will be set, in other words, it'll be 1 if S is less than T. If S is less than T. So that's why it's called set on less than. Set this number if this is less than this. Once I have a set on less than, I can do greater than simply by switching the order of the two numbers. I mean, then it'll be greater than or equal, but that's basically the idea. So that will give me either a 0 or a 1 here in D, and then I can test D with, is it equal to 0? Or I don't need to do the B with the greater than. I'll just do branch equal to 0, branch not equal to 0. I'll just check if it's 0 or not. And then I can check things that are less than or equal to using the pre-existing command. In other words, so to do if I want to do if A is less than 7, I'll have to do first a less than, and then do a branch equal if it's equal to 1, or if I got a true result from the previous. Do I have an example of that from the? No, I don't have an example of that, but this is future stuff we'll look at. These are some pseudo instructions that you can't use. The assembler lets us use non-existent instructions. I told you that. And then translate them for us into real commands. For example, BLT, branch less than. You might, it's not really, it's a pseudo command. Not allowed to use that in the lab. But how would we translate it? It would be set less than. If this is less than, then branch not equal. If the result of that test is 0, if it's not equal to 0, in other words, if it's 1, then jump to the label. So you see, I can translate a BLT into an SLT and a branch not equal. And that's always what it's going to be. You're going to always write it like this: an SLT and then a branch EQ or branch NE. Here's some more pseudo instructions that you might be tempted to use, but you're not allowed to use. Branch greater than, not, branch less than or equal, branch greater than or equal to, set on greater than, negative, absolute. Get the absolute value of a number. You're not allowed to use that. Two more pseudo instructions that you saw are LA and LI. These LA and LI are the only pseudo instructions you're allowed to use. All right, that's it. That's all you need to know now to do the labs. What I want to do is, just a second. I'm going to give you breakout rooms. And if anybody has a question, they can call me through the breakout room. So wait a second. How do I do this? Stop share. And then breakout rooms. Let participants choose rooms. How many of you are there?
16.
Right now, there's 16.
Yeah.
So I'm gonna make 16 breakout rooms. And
What are we doing
Can I
now?
work in groups?
you can work in groups. You can actually work in partners, yes, but I'll make 16, so there's for sure enough. And what you're supposed to do is choose a breakout room that nobody else chose, or actually, if you chose one and somebody else chose, then you'll just find somebody else there. And then work on your homework on the lab, which is lab 1. In the Moodle, it's sitting there. And if you have a question, you can, from your breakout room, say, you can ask me a question and I'll join your breakout room. If you want to have a general question, don't go to the breakout room. You can stay here for a minute. Open all rooms. So yeah, you should be working on your homework. Now, let me stop the recording.